Hey, good morning. Welcome to day 2 of AP Physics. If you recall, yesterday we talked a little bit about velocity, and those of you who are in class did some labs, and those of you who are out of class worked on some problems. And we're going to probably flip-flop that a little bit on Thursday. But what we're going to be looking at right now today is we're going to be looking at building upon velocity and talking about acceleration and how we graph motion. Okay, so we're going to build upon that a little bit. And for some of you, it might seem a little bit like we're putting the cart before the horse a little bit. But don't worry, we're going to kind of clean up whatever stuff we have kind of in the background there. So we're going to have a pretty full day. Just kind of hold on to the rails for a little bit. And we're going to, don't worry, we're going to be applying these ideas over time. So the very first thing to talk about is let's really get a definition of velocity, or acceleration, I should say. And I know you guys know the word acceleration, but I think we're going to understand a little bit better today. And we're going to throw a couple more toolbox equations at you today in terms of that's concerned. But remember that if velocity is going to be changing over time, remember velocity is a vector, not just a scalar. It's a vector. And so when we have this, it includes both a magnitude and, importantly, a direction here. And that's going to be important when we talk about specifically centripetal acceleration. We're going to throw a number of new toolbox equations on the agenda today, and that's because there's going to be several new equations that are going to prove helpful all year long today. So our equation for acceleration is going to be, let's get a little bit highlighter here, is going to be our acceleration is going to equal delta V divided by delta T. So my change in velocity over time. And remember, when we describe our change in velocity, it's going to be V final minus V initial over whatever my change in time is. And if that's the case, I'm going to be measuring my velocity in meters per second and my time in seconds. So acceleration is measured in meters per second, or we can algebraically manipulate this to say acceleration is going to be measured in meters per second squared. So if that's the case, what I'm going to do is I'm going to kind of take some of this out of here, and I'm going to show you that through a little bit of algebraic dexterity, we actually get 3 equations for the price of 1. If acceleration equals my change in velocity divided by time, that means that I can multiply through by t, and I can say that delta v, my change in velocity, is simply going to be acceleration times time. And as a third equation, we get time equals my change in velocity divided by my acceleration. So you get 1, 2, 3 equations for the price of 1. If you feel comfortable just writing in 1 equation, putting that in your toolbox and knowing that you can adjust it to those 2, that's all fine and well. But if you feel more comfortable putting all 3 down, please do that as well. So if I'm graphing acceleration, the way that I'd graph acceleration, or to graph my motion, I would have a displacement versus time graph. And since acceleration, I'm going to choose a slightly different color here to do this. Since acceleration is going to be my change in velocity over time, okay, and really my velocity is going to be a change in displacement divided by time. So if I have this situation right here, a displacement versus time graph, this right here would imply constant acceleration. The fact that that slope is constant means that I've got a constant velocity, and so that means that there's going to be no acceleration in this graph. Okay, that's going to imply a constant velocity because my distance is changing the same amount every bit of time. Okay, that's going to be a constant velocity. Whereas this graph right here would illustrate the fact that my velocity is changing over time. It's got a changing slope. If this slope is changing, then that means that I am accelerating because there's a change in velocity over time. Okay? So That's the way to recognize a displacement versus time graph. So what we're going to look at here is the fact that we can have three different graphs describe the same motion. So I've got three different graphs. This one's a displacement versus time graph. This one's a velocity versus time graph. And this one's an acceleration versus time graph. And I'm just simplifying it by saying A, V, and D. But you guys are smart enough cookies where you should be able to figure that out. So if I have a displacement versus time graph and it slopes upward like this, that means that my velocity is continually increasing over time because my slope is changing here. How would that look on a velocity versus time graph? Well, a velocity versus time graph that would describe that motion would be a straight line. These two would represent the same types of motion. Whereas if you're looking at a acceleration versus time graph, right here, what that would imply is that you've got a line right there. I'm implying constant acceleration because my velocity versus time graph is going to be a straight line, and so that means my acceleration is constant. Now, one nice equation you get from this last graph right here is that if you recall, let's say that this was the amount of time that this happened, and now I can simply measure the area under this line here, and that is actually going to represent my change in velocity, because this rectangle here, if this is 0 for acceleration, this would be a positive value. My change in velocity here would simply be acceleration times time. And that relates to kind of an earlier equation, but if I think about this in another sense, the slope of this line right here, acceleration, is going to be my change in velocity over time. So all I'm doing is taking these two and just kind of flip-flopping them a little bit. If I want my delta V, it's the integral of this, or it's the area underneath this line. If I want the slope of this, that's going to give me the acceleration. Now bear in mind, we can have a negative acceleration. We can put on the brakes, otherwise we'd go driving through every stop sign we have. So if I have a, let's put in a line here to make it a little bit easier. If I have a negative slope of my velocity versus time graph, that's going to give me a negative acceleration. Okay, let me just actually use writing here. That's going to give me a negative acceleration. Okay, that type of graph right there. So we kind of gave you some straightforward equations here, and we're going to build upon that a little bit. Let me pause here for a sec. Just going to draw this down here a little bit. And let's say I have a graph that looks something like this, where I had an initial velocity and I have a final velocity, and that's changed over time here. Now I can actually create a new equation here by doing this. I can say that my final velocity, so this is again another toolbox equation, so we'll put a star by it, equals my initial velocity plus acceleration times time. And the reason why that works is because I have this initial velocity here, that's my starting point, and then if we said before that delta V is going to be acceleration times time, so this will give me that delta V. Okay, if I multiply my slope times this, that's going to give me my final velocity. So I can show that graphically, but also I can figure out my final velocity is going to be that equation. So now let's say I wanted to figure out how far I went if I'm given a velocity versus time graph. So what is my delta x here? Let me get that into pen mode. What is my delta x here? Well, if I want to know what that is, I can figure out that if I have a VI here and a VF that's there, if I just kind of split this difference here, let me put a little red dot here, that's going to be my average velocity over time, because the area above this graph here and the area below this graph here are going to be equal. So my V average is actually going to be VI plus VF divided by 2. So if that's the case, I can then go back to my toolbox and I can say that my delta X here equals 1/2 VI plus VF times time. And that, my friends, is yet another toolbox equation for you to use. And you can see how that works graphically right here. So we said earlier that VF equals VI plus AT. We said that earlier on this page. And now we're saying that delta X equals 1/2 VI plus VF times T. Let's just, for the sake of argument, substitute in for this VF, VI plus AT. So what do we get when that happens? So now we get delta X equals 1/2 times VI plus VI plus AT times T. And what this simplifies into is you get 2VI here plus AT squared. And what this really simplifies down to is delta X. If you have 2VI divided by 2, it ends up being VI plus 1/2 AT squared. So that's another equation. This will tell you how far you go even if you don't know the final velocity. If you're given my initial velocity, my acceleration, and my time, guess what? I can figure out what my displacement is going to be. Now for this next one, don't worry so much about how I derive it. Just realize that I'm trying to get to a final answer here, okay? So if time, let's get here, if time equals my change in velocity divided by my acceleration, that therefore means that I can have, that's the same as saying VF minus VI over acceleration. That's going to be my time, okay? Now, we said earlier that delta X equals VI plus 1/2 AT squared. But we also said that that my delta X equals V average delta T, or VI plus VF divided by 2 times delta T. But we just set up here that delta T could be that. So now I can say that delta X equals VI plus VF over 2 times this value up here, VF minus VI over A. Oops. I'm going to get this 2A out of the denominator, and I'm going to say that 2A delta X equals, and I'm just going to use the fact that I can reverse these two values, not any big deal, VF plus VI times VF minus VI. And you might notice here that this is actually going to be the difference between two squares. So I can say that 2A delta X equals VF squared minus VI squared. And now what I can do is I can toss this VI over on this side and just kind of flip-flop left and right, and I can say that VF squared, my final velocity squared, equals VI squared plus 2A delta X. Now, that took a lot of legwork, but it gave us a rather valuable equation. And what's so valuable about this equation is that it allows us to determine these types of values without even knowing the time that an object has been accelerating. So you tell me that I've got an initial velocity and a final velocity and an acceleration and a displacement. If you give me any three of those four, I can figure out the other value without knowing how long that acceleration even happened. Okay? Now, one thing to bear in mind here, we will never have a changing acceleration in this class. We will also not misspell words like that in this class.